Hi everyone. Today I'm going to give a quick introduction to Vuforia. So we're going to talk about what Vuforia is, what kind of information it gives us, and some logistics behind that, and also possible applications for Vuforia, including applications that I've tested out and have confirmed work. So let's get into it. So what is Vuforia? Vuforia is a computer vision library which is similar to TensorFlow, which we use for object detection, and both are implemented in the FTC SDK. Unlike TensorFlow though, in FTC at least, we use Vuforia mainly for image detection rather than object detection. So as an example, this year we had stacks of rings and we had to determine the height of them. So for that task we used TensorFlow, whereas Vuforia was used to detect the image targets that were attached to the sides of the walls. So this year you might have seen a group of kids playing basketball as one of the image targets, and we use Vuforia for that. But keep in mind that Vuforia, just in general, isn't just used for image detection. Only in FTC we're using it for image detection because we've determined that TensorFlow is just slightly better, or for our purposes, in FTC. So, what kind of information does Vuforia give us? We have the X, Y, and Z position from Vuforia. Now, I will say that the Z position isn't as helpful compared to the X and Y position, just because you won't see the robot moving up and down or vertically in the field. You'll mainly see it moving laterally or staying on the field, so the Z coordinate isn't really that helpful. And for that reason, I like to picture the playing field of FTC more as a 2D plane rather than a 3D space. It's just a lot easier to think of it that way. Vuforia is also able to determine what image it's looking at. So for example, this year we had multiple image targets attached to the sides of the walls. Each of them have their own label, which is determined by Vuforia. So, for example, if Vuforia is detecting a certain image, it might say this image is image 1, whereas if it's looking at a different image, it might say that image is image 2. Just arbitrary names. And then finally, we can determine the heading, pitch, and roll, which are all angles or rotation around certain axes, namely the X, Y, and Z axis or axes. So we're mainly going to be using heading, which is rotation around that Z axis, just because you won't see the robot rotating a lot around the X and Y axis. It's just very rare. We don't really see that kind of stuff in FTC, and honestly I really can't think of a challenge where we've had to use it previously. So there you go, just some information that Vuforia gives us. And just a brief overview of the FTC coordinate system. So at the center, you guys should be able to see my cursor, where the 4 center tiles meet, that would be the origin. So like I was saying before, we can think of the FTC field as a 2-dimensional plane. So at the center would be the origin. Now, something a little bit strange is that the x-axis would be this sort of up and down axis, whereas usually in math classes, for example, we're more used to seeing it as that left and right. Obviously this depends on perspective. Like if I was over here, I'd see that x-axis as that left and right axis, whereas if I'm looking over here where my cursor is, I'd see it as that up and down axis. But yeah, so the origin, just takeaway here is the origin is this 0, 0 coordinate at the center where the 4 center tiles meet. And if I move up, for example, that would increase my x coordinate, and if I move left, that would increase my y coordinate, or at least for this image. And we'll talk about the coordinate system in Ultimate Goal. It's very similar. It's just sort of which way you have to move in order for your y coordinate to increase, and which way you have to move for your x coordinate to increase. But yeah. So, what are some potential applications of Vuforia? So, one potential one is rotating to an image target that you're detecting with your camera. Another would be rotating to a certain angle, since Vuforia is giving us our heading, so we can keep on rotating till we reach a certain heading, and that would be rotating to an angle. You could also move to a certain X, Y, and Z position, but a limitation, just in general for Vuforia and FTC, is that the camera always has to be detecting an image target. Because if it's not detecting an image target, it won't be able to determine all of these orientation details, and it'll be pretty much useless. So that's one thing I have to say about Vuforia, just in general. It should not be used as a independent navigational system. Instead, I'd use it as something you'd want to use in tandem with other navigational systems, such as maybe the IMU in your hub or odometry, if you want to like double check that you're at a certain heading. And like, for example, odometry, maybe let's just say, is reporting that your robot is at a 92-degree heading, and you want to just make sure. You could use Vuforia to determine that. But yeah, as I was saying, just independently, if you want to move around the field, since you always have to be looking at an image target, it's going to be very difficult unless you have multiple cameras. But I don't really see why you'd want to do that, if considering there's just so many more ways to navigate the field with like encoders, odometry, just as examples. So just to take away, don't use Vuforia independently as a navigation system, but can be used as an aid. And yeah. So rotating to an image target, I'm going to just briefly talk about the pseudocode. So I've actually implemented this in FTC. I've coded it all, and I'll be talking about that in a future presentation. For now, I just wanted to give an introduction. So I understand that this image might not be very clear, so I've just pulled it up on a separate screen. Alright, so here, let me zoom in a bit actually. Alright, so here I've labeled the origin. As you can see, it's the where the center 4 tiles meet, so 0, 0. X increasing and decreasing. So okay, I labeled this kind of awkwardly. I don't know why I didn't use axes instead of that, but it's still get the point. If we're moving up, we're going to be increasing from the origin. So if I move up, this would be increasing, 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 and this would be decreasing for the X coordinates. And then starting from here, we're going to be increasing our Y coordinate, and then starting from here, we'd be decreasing our Y coordinate. So let me explain a couple more things in this image. This point that I've labeled XY is just an arbitrary point that our robot could be at. So this little dot that my cursor is hovering over, imagine that as our robot, and it can have any XY coordinates, which is why I've labeled it just as XY. We don't know what it'll be in advance, and that's the sort of the point of this algorithm. We want to rotate to the tower goal from any point without knowing in advance. So arbitrary coordinates XY for our robot, and that's our robot position. The image target position. So let me give some context for this. This rectangle right here that I've drawn in is sort of our tower goal in a two-dimensional plane. And why I've drawn it like this is because right underneath this tower goal, which is one of the objectives of ultimate goal, we want to shoot rings into the tower goal. So right underneath that tower goal, there's actually a image target that's parallel to it. So if we angle ourselves towards that image target, we'd actually be also angling ourselves towards the tower goal, and that would allow us to aim at the tower goal. So, and now for the coordinates of this, I'll explain that in a second. So basically, how I determined it's at this 72, 36, keep in mind x, y. So first I had to find the x coordinate, so starting from 0, 0, each tile is about 24 inches, so keep in mind we're measuring in inches here. So 24 inches, 48 inches, and then 72 inches on the x-axis. So that's how I got this 72. And then 36 is from 1.5 tiles. Excuse me. So 1.5 tiles is about 36 inches, and that's where the center of our image target is. So we'd be, if we correctly rotate to the image target, we'd be aiming around the center of the tower goal, which should be pretty ideal. Theta is just the arbitrary angle that we have to rotate to. So this is our objective. We want to find this. B is, so I've drawn a triangle, a right triangle, to try and determine theta. So in order to make a right angle, we have this coordinate x, 36, and which is, so if I draw a line down all the way, so it's perpendicular to this line that I've drawn from this point, we can sort of create a right triangle, and then if we know B and A, we're able to determine theta by using arctangent. So if we can find the arctangent of B over A, we can find theta. So how do we determine B? Well, since this is at the point 72, this is at the point X, and this is at x, 36, we just, the length of B will just be 72 minus x, and the length of A similarly will just be 36 minus y. And then to find theta, we just have to take the arctangent. Since the tangent of theta would be B over A, the arctangent of B over A would be theta. Hopefully that makes some sort of sense. Sorry if you're not too familiar with trig yet, but basically arctangent, what we're doing is taking a ratio and trying to match that ratio to the angle. So since theta's tangent would be B over A, the arctangent of B over A should give us the angle that we need to rotate to. Hopefully that made some level of sense. If not, I can clarify that with you later. And here I just said we are assuming that the camera is aligned with the center of the launcher. So we have a launcher mounted on our robot. So when we angle our robot towards that image target, we'd actually be angling our camera towards the image target, not necessarily our launcher. So there are things in code which we use to account for this, but for now let's just assume that our camera and launcher are pretty much parallel to each other, so we can disregard that. So this is just the rotating to the tower goal algorithm. Hopefully this diagram was helpful. So go back to the presentation. All right. And then here I've provided the pseudocode for moving to a point. So let's give our robot an arbitrary location and label that x1, y1, and we want to move to point x2, y2. So first we have to compare x1 and x2. If x1 is greater than x2, then we'd have to move backwards, since it would be on that up axis, I guess, up and down axis, it would be sort of above x2, so we'd have to move backwards, and then until they're equal. And otherwise, if it's less than x2, then we'd have to move forwards, and until of course x1 and x2 are equal, and then we'd have reached our desired x location. Similarly, we do the same thing with y1 and y2, except if y1 is greater than y2, we would have to strafe left until they're equal, and otherwise we'd have to strafe right until they're equal. And then after both of those steps are completed, we'd be at our x2 comma y2 location. Once again, if that didn't make sense, I can try and clarify that for you individually, but basically we're moving up and down till our x locations and y locations match our desired coordinates. So by moving up and down, we're increasing and decreasing our x coordinate, and by moving left and right, we're decreasing and increasing our y coordinate. Just some things to keep in mind for this algorithm is that there are actually multiple ways to move to a point. For example, like the most efficient way of getting from one point to another point is just a straight line, not necessarily doing two lines at a time, which is sort of what we did. But that's kind of difficult to do because you'd have to make your robot strafe in a way that it can basically strafe at any angle. But here we're basically our robot would only have to know how to move forwards and backwards and strafe left and right. So it's more or less the simplest way of figuring out how to move to a point. Thank you for watching my presentation, and if you have any questions, I know this was a lot of information and I might not have been very clear about it, so if you have any questions, namely I think that algorithms might be the most difficult part to understand, just let me know and I'll try to clarify that with you. Thank you